Hey everyone, welcome back. In this lecture, we're going to be talking about potential energy, which is just another kind of mechanical energy um, that we'll work with a bit in this class. So let's get started here. I want to begin, though, by talking about conservative forces. Okay, so I know that's not a force that voted for Donald Trump. It means something entirely different in physics. All right, very happy I was able to get my dad joke out of the way there. Okay, so let's say, mathematically speaking, a force is conservative if it can be written as the negative gradient of a potential energy. Potential energy. And I know that, let's see here, that we're supposed to be talking about potential energies, and here I am defining a force in terms of something that we haven't really discussed yet, but I think that there is value to this, and hopefully it all sort of makes sense when we get to the end here. Now, I'm going to copy and paste this into the document here. And so many of you, right, might be looking at this and thinking, well, what the hell does this mean? And that's a perfectly valid question. So in vector calculus, there's this idea of a gradient, right? And it sounds really complicated, but it's actually not that bad. All it says is it's like this vector operation, right, where we apply it to a scalar function and we turn it into a vector. And so the gradient of u without the negative sign in front would just be the vector with the derivative of u with respect to x as its first component, the derivative of u with respect to y as its second component, and the derivative of u with respect to z as its third component. We typically write derivatives of a function that depends on more than one variable with this weird d symbol, but it is, for all intents and purposes, the exact same thing as a one-dimensional derivative that we've worked with a little bit and are hopefully familiar with. And so don't worry so much about this. It's just something that I feel like I should mention. This next thing, though, will be a little more useful for our purposes, and so I'm going to say that in the one-dimensional case, we have this, and I will copy and paste this too, because it would be a bit to type with the formatting and everything. And so we see, right, that this is kind of like, we can think of this as just the x component of this equation here, and hopefully this makes the idea of a gradient a little more clear. But the x component of a force, right, is just going to be given by the negative derivative of the potential, which I know we still haven't defined yet, with respect to x. Anyway, this suggests, right, and this is actually where we can kind of maybe start to see what these potential energies might look like, is that we can just, take the negative of the integral of the force with respect to x and recover the potential function, right? And so I'm going to say we'll return to this idea later. But what's important for now is the idea that the work done on an object by a conservative force depends only on the initial and final positions of the object. I'm going to put a box around this because it's actually a really important idea. I think I'm going to start boxing things that are important. I don't want borders though, just outside. Okay, why is this being dumb? Let me get rid of those then. I don't want to mess with this right now. I just clicked no border. Okay, well that's going to stay like it is. Uh, I don't like it, but it's still true, right? Regardless of whether it's boxed in a way that I don't like. Um, okay, so let's look at what this looks like for, say, the spring force, right? Uh, we're going to talk next about elastic potential energy. And so I'm going to say recall that Hooke's law states that f sub x equals negative kx, right? This is a little bit different than I wrote it previously, so I'm just going to also say that when written this way, it's understood that x indicates the displacement from the equilibrium position, right? From the spring's equilibrium position. Because remember that we're imagining a spring being stretched out or compressed, right? And also remember that springs have equilibrium lengths, right? This is just like sort of the length that the spring is when it's just, chilling, right? When it's not being extended or compressed. Okay, so what happens though if we integrate this force with respect to x, right? So let's do it, and we're gonna use this little physics trick where we just put in the appropriate limits of integration so we don't wind up with a constant, right? Because when we do an indefinite integral, we wind up with a constant, but doing it this way, we get the form of the elastic potential energy that we want. And so just to remind you, right, mathematically it would be bad form if I wrote the same x here and here as I did in the upper limit of integration. So that's why it just looks different. It's just a script x, right? It's a dummy variable, but it's not a huge deal. I feel like I'm kind of flip-flopping between trying to keep the mathematicians happy and angering them. So I don't know, maybe it just balances out to neutral in the end. Anyway, so we find, right, that we can, let me put this in words, we find that we can define the elastic potential energy, that's what we call this, right, of a spring as, and let me do this, I'm going to say U sub E for elastic, right? And this is defined to be 1/2 k x squared, right? Where x again indicates the displacement from the spring's equilibrium position. Okay, so we now know what sort of, like, one of these potential energies looks like for a spring, right? That's what this is. And so I'm also going to just say that this, as you should check, has dimensions of energy, and the appropriate unit is the joule. Okay, probably nothing surprising about that. And that is also sort of suggesting that we can combine this with something like kinetic energy and work, right? Because all these things, they have the same dimensions and the same units. And so that's usually an indicator that we can work with them together, right? So let's look at an example of this, and we're going to do this two ways. We're going to do it the hard way, and then we're going to do it the easy way. So hopefully I can convince you that there's some value to this idea that we discussed about conservative forces and how we can calculate the work that they do, right? So the first thing is we could do this directly via integration, right? From the expression that we saw earlier for work, right? This was in the last lecture. And I'm going to copy and paste this because it would be a good deal to type. But what we do is we just integrate the force, right, from 0 to L, right, because the initial compression or extension of the spring is 0, and then it's now extended to L. Well, it's extended L past the equilibrium position. This is just the force, right? And we find that the work done here is just given by 1/2 k L squared, right? And remember that the sign here, the SIGN, makes sense because if you imagine like grabbing a spring by its end and pulling it, right? The end of the spring moves in the same direction as the force that you have to apply to extend it, right? And so we would expect this to be positive work. I am very much in the habit of not even writing the cosine in the definition of work because oftentimes it will either just be cosine of 0 or cosine of 180 degrees. I think that can be confusing for people, so I will try to avoid doing it, but it's a pretty deeply ingrained habit at this point. So if you want to do that too, that's totally fine. You just have to, always be thinking about how the direction of the force vector compares to the direction of the displacement vector for calculating work, right? Okay, so I'm going to say then that we should note that this is simply the change in elastic potential energy of the spring, right? Because let's say delta U sub E is, well, the final elastic potential energy, as we've defined elastic potential energy, is just 1/2 k L squared. And remember that initially it was at its equilibrium length. So the initial elastic potential energy is just 1/2 k and then 0 squared, right? And so we find it just works out to be the 1/2 k L squared that we found via the integral, right? And this is not just a coincidence. This is a thing that happens with conservative forces, right? And that's why we like conservative forces, because they're easy to do calculations with. Okay, cool. So hopefully this sort of gives you an idea of how calculations can be simplified for things like work when we're doing problems involving conservative forces. Okay. I don't think that there's really anything else I want to say about elastic potential energy at this time. I should just, in case I haven't mentioned it, say that it is another form of mechanical energy, right? So we have kinetic energy, that's considered mechanical energy. The elastic potential energy, which is also considered mechanical energy, and gravitational potential energy, which we'll get to very soon, is also considered mechanical energy. And I believe the reason for that word, or that phrase, is that this particular topic that we're basically focusing on for this semester within physics is called mechanics, right? So it just sort of makes sense. Okay, cool. So let's talk about gravitational potential energy now. And I'm going to say that for the time being, we'll define the gravitational potential energy of an object to be, and I'll write this as U sub g, and it's a function of the y position of the object, and it's just mgy. Now I should say that, let me write this out, as we'll see later on, this is an approximation that only really works when we're near the surface of the Earth or any other planet, right? With the appropriate value of g. I mean, I don't know. Maybe one of you is going to go to Mars someday, right? So gravitational acceleration is different there. So there's that. And I should say that the reason we'll see that this is an approximation has to do with Newton's law of universal gravitation, which we won't cover for a little while. So we'll just have to hold off on that. But if you can just take it on faith for the time being that this is appropriate, we'll be fine. Okay, so I do have a very important disclaimer about gravitational potential energy. I'm going to put this in the document. I'm going to say that an extremely important conceptual idea is that specific values of gravitational potential energy in and of themselves are not meaningful. What is meaningful is a change in gravitational potential energy. And so I really want everybody to remember this. And for the time being, I'm just going to assert it and hope that you believe me. But I will likely give you a homework problem that has to deal with this so you can kind of really see how it works in practice. And we'll do an example too, but this might not make it as clear as the homework problem I have in mind. So let's look at this example. Your physics textbook with a mass of 1.5 kilograms is at rest on your desk, which has a height of 1 meter, right? Above the ground, or above the floor in your apartment or house. What is its gravitational potential energy? The answer is that it depends. And this has everything to do with what I was just saying, right? About specific values of gravitational potential energy not being meaningful in and of themselves. So let's look at a few different ways we could evaluate the gravitational potential energy, bearing this in mind. So if we define y equals 0 to be at the floor in your house or apartment, then the gravitational potential energy of the textbook is this. It's just mgh, and numerically this is about 14.7 joules. Okay, so far nothing surprising, and this probably seems like a reasonable value to obtain, but let's say you live on the 3rd floor, right? And let's say that the 3rd floor is at about a height of 9 meters. And now we define y equals 0 to be at the ground outside your building. Then in this case, the gravitational potential energy is this, right? It's going to be mg big H plus little h. And this numerically will evaluate to be about 147 joules, right? So that is 10 times as much. So that's kind of interesting. You know, I'm telling you that this is not a particularly meaningful number, but we find that we can, you know, all willy-nilly basically multiply it by 10, right? And I mean, we could multiply it by 1,000, as long as we're still close enough to the surface of the Earth. Anyway, the last thing I want to say is now, if your building, right, is 5 stories high, and I'll denote this with a fancy H. Haven't really been using as many fancy letters as I would like to. And you're on the roof and decide to set y equals 0 there, the gravitational potential energy of the textbook would be negative, right? And you could calculate this based on, I think, all the information we have. So, you know, I'm not going to get the number here, but I think you see where I'm going with this, right? Is that it's all sort of just a matter of where you decide to set your y equals 0. And deciding where to set your y equals 0 is one of the first things you should do whenever you're solving a problem involving conservation of energy. So I'm going to put that in the document here. I'm going to say that this suggests that whenever you're solving a problem that involves gravitational potential energy, one of the first things to do is define where you're taking y equals 0, right? And this is like what we talked about before with reference frames and defining your origin. That is all I'm going to say about this for the time being. We're going to look at some examples in a little bit here, but first I want to talk about non-conservative forces. And there isn't really any equation to write down for non-conservative forces that we haven't already written down, but I just want you to start thinking about, you know, which of the forces that we're working with are conservative and which are non-conservative. So I'm going to say for a non-conservative force, the work done on an object does depend on the path taken by the object as the force is being applied to it. I don't remember if I used the word path in my discussion of conservative forces, but remember that we did certainly say that the work done in that case only depends on the initial and final position of the object. And so another way of saying that is that there is a path independence to the work done on a conservative, or the work done on an object by a conservative force, right? And so that's why I'm phrasing this way, because for a non-conservative force, it's the opposite. So let me give you some examples of non-conservative forces. And these are friction, air resistance, any force that you as a human could apply, etc., right? So most of the forces that well, I don't know about most, but I would say we deal with more non-conservative forces than we do conservative forces, right? And really the only two conservative forces that we have for the time being are the gravitational force and the spring force. So if a force that you're working with is neither of those, then odds are it's non-conservative. Okay. So let's just look ahead a little bit. There is this idea of conservation of mechanical energy, right? I think I mentioned this when I first discussed energy. And we're now, right, we're now in a position to write an expression for the total mechanical energy of an object. So we denote this with a capital E, and the total mechanical energy is just the kinetic energy plus the gravitational potential energy plus the elastic potential energy. Now, this is general, right? And an object doesn't have to have elastic potential energy, for instance. Like that, is something you'll see very often, right? We'll see that in the example we're going to do. But if you have like a spring in the problem, then it's a good indicator that there will be elastic potential energy. And if you have a change in height of some kind, that's a good indicator that you want to think about gravitational potential energy. And finally, if the object is moving, if it has some velocity, then you want to be thinking about kinetic energy. So perhaps we can imagine a situation where all three of these forms of energy present themselves, right? And so I would say maybe think about like, a small spring, right? That's fixed to the ground. Maybe I'll make a sketch of this. That might be the way to go here. Okay, so we're talking about, just as an example, right? Like a spring that's fixed to the ground, and you compress it by putting maybe like a marble or something on it, right? Like that. And then you let it go, right? So you're holding it down, then you let it go, and I think we all kind of can envision what's going to happen here. It's just the spring is going to extend, and it's going to, sort of probably shoot the marble up into the air. And notice that in this problem, or in this scenario, we have a spring, so elastic potential energy is something we want to think about. We have that the marble's height is changing, so gravitational potential energy is probably something we want to think about. And the marble is moving, right? It has a velocity. And so kinetic energy is something we probably want to think about. But just to reiterate, it doesn't mean that we're always going to have all three of these things in a given problem. But anyway, remember that if we plug in what we have now found all these different quantities to be, kinetic energy is just 1/2 mv squared, right? Gravitational potential energy is mgy, and elastic potential energy is 1/2 k x squared. So this is a general expression for the total mechanical energy of an object. And so you might be asking, why do we care, right? Maybe you've been asking that all along. I hope not. But in this particular case, we care because in systems where non-conservative forces are absent, energy is conserved, right? So let me put that in the document here. And I'm going to say in systems where non-conservative forces are absent, this is a conserved quantity, right? And what that means is that, if you look at it at some, like say time t equals 0, right, this expression, it could be some number. I mean, it will be some number, right? And then if you look at it later on, right, you might have a different velocity, you might have a different height, you might have a different compression or extension of the spring, but it will still evaluate to be the same number in the absence of conservative forces, right? And so the conservation of energy expression, and this is a lot to write, so I'm just going to copy and paste it, try to give you some time to get it all down, is this, right? We just have, for instance, the initial mechanical energy, and we fill that in explicitly, and we find, we can write it like this, equals the final mechanical energy, which we just call E without a subscript. And what is going on, right? I mentioned this before, but I really want to stress this, is that, for instance, we might start off with, say, some expression for mechanical energy that looks like this. And so if we know, for instance, right, that like later on the velocity is larger, then there has to be some corresponding change in these other two things, right? In the say, the gravitational potential energy or the elastic potential energy to sort of counteract that and make sure that whatever number we found the initial mechanical energy to be, the final mechanical energy is still that same number. It's just the proportions might have changed, right? So we might initially have a large amount of kinetic energy and then at some time later have a very small amount of kinetic energy, and that just means that to compensate for that, the gravitational potential energy and the elastic potential energy possibly would have had to increase, right? And we'll talk about this more. I will start the next lecture with a review of this idea and go into probably some more detail, just because I know that this is something that can trip people up the first time they see it. But yeah, we'll come back to that. I just want to wrap up with an example here, right? And this is going to be another sort of, well, let's use these ideas to confirm what we know about kinematics. So we want to derive an expression for the maximum height attained by a projectile launched from the ground with some initial velocity v0 at an angle theta above the horizontal. And we're going to ignore air resistance pretty much as always. So here, it's a good idea just to stop and think about which forms of energy we are dealing with, right? And there's no mention of the spring in the problem, and so it seems like we're just going to probably be concerned with kinetic energy and gravitational potential energy, and that is indeed the case here. So if we define y equals 0 to be at ground level, then the initial mechanical energy is just going to be the initial gravitational potential energy plus the initial kinetic energy, right? But the initial gravitational potential energy by our choice is 0 here. However, the kinetic energy is not, right? So we find that the initial mechanical energy is just determined by the initial kinetic energy. Okay, so then let's think now about what's going on when the projectile is at its maximum height above the ground, right? And so I'll say that at the projectile's maximum height, and we'll say that this is, we'll call the maximum height capital H. The mechanical energy is 1/2 m v squared, right, plus mgh. And if we had numbers, say we had a mass, say we had an angle, say we had initial velocity, and I guess a maximum height, what we would find is that when we calculate this number and we calculate this number, that they're the same, right? And that's because we have no non-conservative forces doing work, so conservation of energy applies here. Anyway, we have to now think back to what we know about kinematics, right? And I'm going to say from kinematics, we remember that at y equals big H, the velocity vector of the projectile is, and we're going to say that it's v initial, right? Because remember, one of the big ideas about projectile motion was that the x component of velocity doesn't change, and this is a vector. And we could write this explicitly by using cosine. We just write cosine theta, and then the y component is, as always, 0 at the maximum height, right? So you might be wondering why we're doing this, but we are going somewhere, I promise. The mechanical energy can be re-expressed as 1/2 m v0 squared cosine squared of theta, right? And we don't do anything to the mgh term, that's just what it was before. So conservation of energy, right? Remember, equating the initial mechanical energy to the final mechanical energy gives, and we would write this out like this maybe, say initial mechanical energy equals final mechanical energy, and then remember that the initial mechanical energy was just kinetic, so that's what that looks like, and then we just found that the final mechanical energy would be this. And then from this, right after we go through and solve, like one of the first things you might notice is that the masses cancel, and that's good because remember in kinematics, all of our equations had no mention of mass, right? So it would be startling if the mass didn't cancel out here. But anyway, what you end up finding after you solve for H algebraically is something like this. Okay, and then I'm going to write this one more time a little more suggestively. And this is our expression for the maximum height. But remember that sine squared theta plus cosine squared of theta, this is one of the trig identities we had, is 1. And so we can get rid of the 1 minus cosine squared of theta in favor of just sine squared of theta, right? And so upon substituting this in, we find that the height, the maximum height the projectile attains, is v initial squared sine squared theta over 2g. But remember that this term in the numerator here is just the y component of the velocity squared, right? And this is exactly what we found from kinematics. So yay, physics works, right? It's consistent, and we'll continue to see that it's consistent. Okay, that's it for this lecture. I will see you in the next one.